Okay, so this presentation is about bridging the divide between surveys and simulations, and this is going to be in Cytos style. And a few people here have asked me, like, yeah, great, what is Cytos? So I guess we are the new kids on the block. We do Wi-Fi design tools, think planner, think survey devices. And some people ask, like, can you buy it? Yes, mass-produced, not 3D printed, mass production. We have customers, we're selling this stuff, so if you find it interesting, find us. But let's move forward. Very short intro. So my name is Mika Hakala. I'm a founder, CEO of Cytos, and I have about 15 years of experience designing wireless devices and software. And some of you may know I used to work with Ekahau, head of R&D and CEO of Ekahau for some time, several years actually. And before that, I did some real engineering work, so I designed wireless chipsets. So I do love RF and L1, so if you want to talk physical layer, I'm game. So let me start by doing some myth busting that's very relevant to this topic. So the first myth is that you'll get accurate measurements with your whatever device you are using because the vendor said that their device is accurate. And I have half of my professional career I've been designing these devices, and I'm telling you it's very difficult to build a device that has a good antenna pattern. And if you don't have a good antenna pattern, you're not going to have an accurate measurement device. And one of the biggest reasons why it's so difficult is that you have ground planes. And if you don't know what ground plane is, it's like when you do modern electronics, you use multi-layer printed circuit boards. And you typically dedicate like one copper layer completely for ground. And why do you do that? Because you need to control the interference coming out of the chip so that you can pass the FCC and CE certification testing in the next phase before you go to mass production. So all good, except when you start placing antennas on that printed circuit board or near it. And like I was doing the antenna stuff yesterday with Jim Palmer, and it's a great one if you want to do it. Like you learn amazing things. Some of them actually have something to do with antennas, but like I'm telling you that like if you place antennas close to a big ground plane, it's almost impossible for an antenna to hear equally well towards the open space and through a grounded copper plate. Okay, so that's a bit of a challenge. And when we were designing this device, we call it the Wave. This is our survey device. We kind of knew this. So what we did is we placed the battery and the electronics and the cooling elements down here, and with the antennas up here. And there's no metal up here, not even screws. So you can see the screws in back, but not up here. And like we took this into our RF chamber, measured it, and like shouldn't be a surprise to anyone, but it performs really well. But unless you build Wi-Fi networks for anechoic chambers, which no one does, then that's not enough. But you actually have to perform in the real world. So here you see some real world measurements. I did this a couple of weeks ago. Carpeted office space. I put this in a test rig. It rotates the device like this, 360 degrees. And then I collect about 700 beacons coming from one access point, okay? And here you see an azimuth antenna pattern done with this particular device here. So the same representation, you can see it's pretty circle. There's some outliers, but it's a pretty perfect circle. The same data is in the histogram, and at the bottom, there are small numbers. This is not made with PowerPoint. This comes out of a measurement software. So there's small numbers, but you see these bins of certain RSSI reading, and the height of the bar is like how many readings did I get? And all the readings pretty much are within plus minus 1 decibel. Okay, so when you rotate this, the results are within plus minus 1 decibel. Why is it important? Because if there's an AP in there and it creates a field here that I want to measure, this device needs to return the same RSSI value whether I'm holding it this way or this way or this way. That's why it's important. But that's not enough, because this is not serving anything by itself. I hoped it did, but I waited for a couple of days and didn't do anything. So I actually have to go with the device. So for a test rig, I was standing on the test rig with this device and rotated the whole thing, like myself and the device. And you can start seeing when I wear this Cytos style, you guys seen me and Konstantin walk around these things wearing like this. you see the antenna pattern is getting a little bit wider because my neck sometimes comes on the line of the line of sight between me, the device and the AP. But we're still within like plus minus 3-4 dBs, and there's something that represents a distribution of some kind. When you have distribution, you can bring math in. So this is one thing, but some people say that you can wear your device any way you want, and so I tried it. If I wear it on my belt, things get a little bit difficult. So now I'm like hardly within 15 decibels, okay? So you can see from the antenna pattern where the device is in front of me towards the AP or behind me. Well, when I saw this, it kind of made me think, like, what did I have for lunch anyways? But all this attenuation is from my body, okay? Because you saw the other one where my body is not around, this is good device. Here, the device is not any different, but it's my body attenuating. So I guess if the myth is that you're gonna get accurate measurements because the device is accurate, I'd say this one is busted because it's necessary to have an accurate device, but you also need to wear it and use it properly. And I just want to say this so you're aware that whatever readings you get depends on quite a bit on how you use your device. So the next one is that signal strength changes smoothly. And what I mean by this is that we can't see RF, okay? So when we look at heat maps, they always come from either planners or they come from survey tools, and they always look smooth. So you have green, and then it goes yellow, and then it goes red, whatever color scheme you use. And it kind of makes you think that the field is like even. So I did this test for purposes of this presentation. I put an AP on a stick. I went 9 meters away, so it's 9 meters from me. I put a servo track, and I set an antenna on that track, and I send it traveling 50 centimeters, okay? And the AP transmit power remains static, and because it's 9 meters away, the distance between me and the AP, or the antenna and the AP, changes only by about 3 millimeters, and the angle remains the same, so we don't have an antenna pattern on the way. So in perfect world, all RSSI readings should be the same, right? Same TX power, same distance, same angle, same RSSI, yeah? Well, RF is weird, so this is what I measured. So on the top, you see the displacement from the center point, so half a meter, and this is the RSSI changes. And there's a spot somewhere around here, where within 10 centimeters, I can record anywhere from -48 to -40. And because this is constructive and destructive multipath, it's not time variant. Unless the building changes, which it doesn't, I can stop and I can measure for average for a long time and get -48. Then I give this to Keith, and he stands in the same spot, except at 2 inches or 6 centimeters this way, and he measures and gets -40. Then we argue for an hour which one of us don't know how to measure, and I'm not presenting here next year. So, but we are both wrong and we are both right. It's these tiny ripples in this field that we see here, okay? So the myth at signal strength changes smoothly, and therefore you can define it accurately is not true. It's busted. So because of the multipath, whatever RSSI measurement you have to think about it as a sample of a distribution. Okay, it's a sample of a distribution. The next one is that survey heat maps accurately represent the reality. So I don't know about you guys, but I've been in many situations with someone that we are looking at the heat map and we are pointing finger at it and we are saying that, okay, what is this? And then we conclude that, well, it must be true because we measured it. Measured must be true, okay? So Peter Mackenzie might say that packets don't lie, but I'm telling you that survey results do, heat maps do. And why is this? It's because you think this is what you measured, but actually that's what you measured. You can't measure anywhere else except where you walk. And you don't even measure the whole track, but you take a small chunk in space, 3D space, like an apple-size sample. Then you move forward and you take another sample. But heat map like that, it's not even a heat map. It's useless, right? You can't see anything, and your customer couldn't see, anything either. So what tool vendors do is that they take those color points and they interpolate and they extrapolate around them so that you get color, okay? But the weird thing is that these tools, all of them, they interpolate and extrapolate too little and too much at the same time. And what I mean by that is that, let's say that I'm in this open space here, it's athletic training area. And if there's an AP here, and I measure green here, and I measure green here, and I measure green here, as a human being, I know it's all green. But I still need to walk all of it properly, because otherwise I don't get the whole heat map, right? So I would like to go to my tool and say, hey, tool, can you please extrapolate more, so I don't have to walk that much? But then I have another problem, which is that in this kind of area, it's a little bit difficult to see because it's small, but I could only walk on this side of the wall, not on this side of the wall. So it's already extrapolating the green color through the wall, and if I extrapolate any more, in here, my customer would probably be like, hey, oh, great, I didn't know I have Wi-Fi on the terrace. But you don't because it's a steel wall, right? But the tool would extrapolate there. So these tools, they do their best, but they don't have an understanding of the context. And if the myth is that because it's a survey heat map, it's real and it's reality, I'd say it's busted, because the tools make about 99.9% of all the colors you see are made up by the tool. And it's really more like color blending than anything else, because the tool doesn't have a context what's happening in real life, okay? So the last myth is that you can't do what-if analysis with surveys. I'd say hold my beer. So demo time. And before I run the demo, I need to explain a couple things so that you understand what you're seeing, because we are doing things slightly differently. So Sidus also has survey planner, like a predictive side of things. We have surveys. And in the beginning, we tried to reconcile the two. Didn't go too well. We had a lot of data, and we were like, what's going on in here? And the problem reconciling these two is that initially we thought that the survey is real, but we just saw that 99.9% of the colors are made up. So we realized that we need a third entity. So we have a planner, we have survey, but we need the third one, which is a digital model of the real world. The only problem being, where can I get this digital model? So long story short, we made an AI engine, generative AI engine, and we dump stuff into that engine. We give it floor plans, and we give laws of physics, like free space path laws and whatnot. And then we give the tool all the survey results, the XYZ coordinates and RSSI values, with one important distinction. We tell the tool that, hey, you can't trust any of these numbers, because if it was measured this much this way, it would be 3 dB different. So we give it a distribution and say, hey, treat them as a sample out of a distribution. And then it starts learning, and AI is kind of weird, so sometimes I, just for the heck of it, I stop it real early in the beginning when it starts learning, and the heat maps, they look like Salvador Dali, it's like oil and red wine on canvas or something real weird. But if you let it learn properly, then it can answer questions that it didn't have in the training material. That's kind of definition of generative AI. So I'm, no guts, no glory. I'm going to do a live demo, beta product from staging environment that's running somewhere in North America. So what could possibly go wrong, huh? So this is the Sidus tool. The way we have set up things is here on the left, you have your filters and, select networks, bands, APs, whatever. Here you have the views, coverage, secondary coverage, interference. And if there are any details, they will show up here at the right. And this is a survey I did in a 6-story office building. This is the 3rd floor. And you see the blue track here, that's where I walked. I couldn't enter most of the rooms. Maybe you guys always have a key to places. I didn't in this particular case. And now, just as tools do, you know how this works, but because I couldn't walk on both sides of the wall, then the tool just expands the colors of my survey points. Now we have this cool button here called Sidus mode, and what this does is when I press it, I'm no longer looking at measured results. None of the results are measured, it's all AI generated, okay? And now if the AI did good job, and if the model works, and if our thingy actually does some good work, what starts happening is that if you look along this track, the colors of the survey heat map and the model should match, right? Because otherwise the system didn't work. So let's press it. Boom. Let me go back and forth a few times and just follow the blue track with your eye and see how the colors of the digital model and the survey match. There are tiny differences in this area, if you look at it, but it works pretty well. Another thing that you start seeing is that in the traditional surveys, these colors bleed out because there's no concept of walls, there's no context, and also because I couldn't enter these rooms, like I have no idea what's in here. But because the AI figured out the walls and stuff, it's able to tell me RSSI values in these rooms. It gives me colors here. And you can start seeing that it understands how walls operate and work, so signal actually gets contained as it should, right? Let's look at another example, like another floor. You can pick up one AP, for example. This is surveyed. This is the digital model. So again, follow the track with your eye. You can see that there's some differences in this area. We're a little conservative on corridors when it comes to reflections. So I was actually measuring slightly higher values than the AI engine predicts. But anywhere else along the track, you can see that things are, the colors seem to match pretty well. And actually, if you look at like this, you know that this is not real. The signal would not behave like this. I couldn't survey on this side. So this is what tools do. But when I turn on the AI engine, you can see that it understands that, okay, this is a wall. These are walls. And the signals start behaving as you would expect them to. So moving forward, I'm running out of time soon, so I'm going to show you the cool stuff. So since I now have a digital model of things, what I can do is I can throw any kind of questions at the AI engine, and it's able to answer because it learned the building. So I can select an AP, let's select this one. And remember, I didn't build a planar model. This is not predictive. I didn't enter any one wall attenuation, 0 wall attenuation. I didn't say, this is a cinder block, this is a dry wall. I didn't do any of it. This is a survey. I can select this AP, and there you go. As you can see, the engine figured out how the building works, and it's able to answer me questions like, if I place an AP here, what would the heat map look like? And we don't make up any of the wall stuff. So there are places like this. The AI couldn't resolve the walls. It couldn't measure because I didn't walk enough around it. So it's only going to say that if you drop an AP here, this one room will have phenomenal Wi-Fi. I don't know anything about anything else. But what you can do is like I can literally then dump these APs out of here. So let's do this. So I'll move them, literally move all of these out of the building, for example. I could delete them, but this is more fun because you rarely get to literally throw the old vendor out. And now I have only the AI model, right? So now what I can do is, let's start adding APs. So now I have a planar capability, but again, this is based on real measurements. All the walls, everything. I didn't enter a single wall material into the tool. It's all based on the surveys, right? So now I can say, okay, well, I can drop in new APs, add APs, remove APs, build walls, remove walls. I can do anything with it because every element has been built into this digital model. And if I give it information, it relearns it. If I know better, like it says that this wall is 6.2, and I said, no, it's 3, I know better. I never have been able to, but if I knew it, I enter 3, and after that, it learns it and takes it as a fact, and off we go. So this is what it looks like, and now I'm going to wrap up before Keith throws me out. So in summary, so we have a solution. We have the most accurate and fastest measurement device on the market. We had to build it because we need very accurate measurements, and we need a lot of measurements for the digital AI machine to have enough stuff to learn from. And then we created this generative AI engine, and it learns the site, and it starts understanding in 3D how the building works. And after that, you can start throwing questions at it, like what would happen if this AP was here, if this wall was gone, if I built wall here, if all these questions, and it's able to answer those things. So where does this land? Well, I guess today you have predictive planners. They're less accurate, but they're faster to use. And then AP on a stick, like you can't get more accurate than that because, I mean, it's real, but it takes more time. So ours lands actually very close to the AP on a stick in terms of accuracy, because it's based on the same results. It's based on real measurements, not you telling which wall is drywall and what is cinder block and whatnot. But it's much faster than predictive, because this example, 6 floors, 300 walls, I entered 0 wall materials into that thing. So it's kind of like a planner, but the AI fills all the blanks that you don't want to. If you want to enter wall materials one by one like you do today, be my guest. If you don't want to, it will figure them out. And all of this AI stuff is in beta phase now, so it's becoming available to our customers today. But the survey side and the planner side, in a sort of more traditional sense, all of this is in production and available today. So if you want to talk RF, great. If you want to talk about this, find me or Konstantin. And like, if you think AI doesn't have any room in Wi-Fi world, subscribe to our blog and at least keep an eye what's happening on this side of the world. So that's it. Thank you.